page. We're going to come back to it. I skipped that page.
Hey everyone, this is Mr. Hausen. We're going to take a look at circuits in a little more detail now. We've heard about some key ideas, and the key ideas that we've heard about are these quantities that are measured in a circuit. And one of them is electric current. Its symbol is I, and it means the movement of charges, right, per second. So when you measure those, right, when you measure the movement of charges, you get amperes. So if you have 6 coulombs of charge flowing past a point in a circuit in 1 second, you have 6 amperes or 6 amps of current. The formula for current is I equals Q, which stands for charge, divided by time. And we've already done an assignment about that. That was a key one. But then recently, we've also introduced voltage. So there's 1 current, and then there's 2 voltage. Now, voltage is one of the hardest ideas in physics, even though we've all heard of volts. And voltage is the phenomenon. Its symbol is a V. And what it really means is how much energy is there per charge. So each individual electron that's in a wire by itself is not a lot of charge, a single electron. But if you have a whole bunch of them carrying energy, and remember the little cartoon we talked about, what if this was a stick figure, right? This electron was a little dude, and it could carry energy in a bucket on top of its head or in a backpack. So that's what I want you to think of when I want you to think of voltage. So 5 volts means they carry 5 joules of energy per 1 coulomb of charge. Okay, but who has more energy, 5 volts or a 9-volt battery? Almost all of us have seen a 9-volt battery. They're rectangular. They have a positive terminal and negative terminal, and they kind of go in. And the most common thing that everyone knows about are probably smoke detectors, right? So 9-volt batteries. Car batteries are even more than that. They go up to as high as 12 volt, and they've got usually 2 posts. But what all batteries have in common is they have to have a high energy side and a low energy side. Okay, so what that allows us to realize now, if the two ideas of current and voltage, is we can now look at a circuit and talk about what it means to be in a circuit. So I hope in middle school there was some experiments that you did, but that was a long time ago. And you probably figured out that you need to have 3 things in a circuit, whether you've done any wiring or only simulations in the past. You need an energy. You need a supply of energy. No circuit runs without a supply of energy. Many of us plug things into the walls, but the battery is the best way to do that. Batteries create energy that flows from the positive terminal, right, where there's high energy, and the energy goes in the wire, carried by the electrons. And it's a one-way trip. What I mean by that is that once it gets to the light bulb, or to the motor, or to the speaker, that energy now goes out into the world. Maybe that's charging up your phone, and your phone now gives off light because you have the flashlight turned on, or it gives off music, because all of those are forms of energy. What never goes back to the battery is energy. It's a one-way trip, okay? So the first thing we need is we need a source of energy. Check, got the battery going. Now we need wires. We need wires because the wires are loaded with electrons. They're made of metal. All wires, well, yep, all wires, we're going to say, are filled with electrons that are loose. They can be pushed around really easily, and it's those electrons that carry the energy. Okay. And the third thing we need, even though it's listed together, is we need something like a bulb, right? So the third thing is a bulb. And what that bulb does is it turns electrical energy into something else. We call that a transformation. So that something else can be light, or it could be sound, or it could be a motor and turn it into some movement. So what are the three things a circuit absolutely needs? Number one, it needs an energy supply, and you should link that to the battery. You need wires, and that's right here in the circuit, right? There's our wires hooked up to both ends of our battery. And then lastly, we need something called like a bulb to take the energy and turn it into something else. So an energy source, a conductor, and a bulb. You may hear me use the word load because it means anything you hook up to a battery. Okay. Now, the other key idea besides an energy source, wires, and an energy device that takes the energy is it has to be in a loop. You can't have any breaks in the wires. If you are connecting them with little clamps, they have to be tight. If you're doing something called soldering, a few of you have heard of soldering. That's when you melt metal to make an electrical connection. And well, you better know what you're doing and make sure the metal melts exactly where it should be, okay? So that's what a circuit has to have. All circuits have to have those three basic components. Okay, now a quick lesson here, keep going, on circuit symbols. When you're drawing a circuit or seeing a circuit, there's certain symbols that are always used. Sometimes they might be called a schematic drawing, which is like got the word scheme in it. It means whenever you want to draw a battery, you draw this symbol: wire, long line, short line, wire. And then you can connect it to as many other wires as you want. But the part that's a battery is the long line followed by the short line. Let's zoom in on that. Well, a wire is always drawn as a straight line. You never bend them. And they can take 90-degree turns where you connect them, but they will never form like curves. Okay, so here's a light bulb. Light bulbs are a circle that represents the glass part. And I bet some of you have heard the fancy word, a filament. That's what that thing stands for in the middle. So a light bulb is a circle with a loop in it. Okay, great. That's a very common piece of a circuit. And then the last part of a circuit that's incredibly common is something called a resistor. And a resistor, you've seen them if you've ever seen a circuit board. In fact, here is a perfect picture of a resistor. They don't look like they do anything important, but what they're doing is they are controlling the flow. Think about something that resists you, like maybe if you've ever been to a restaurant or maybe seen one at a bar that's near a restaurant. Isn't there a person that's called the bouncer, and they kind of keep the flow of the people in control, going in and out of a probably a over 21 kind of club. And so this resistor, you put it in your circuit, and what it does is it makes sure that there's just the right amount of current going to your light bulb, because too much current and light bulbs can pop. It damages the filament. And what would be a better shape for a resistor than like a zigzag? Like imagine if you were trying to run down like a football field, a soccer field, if you play any sports or something like that, and someone said, okay, well, I have to slow this person down. Well, what's a great way to slow something down is a zigzag. They have to keep turning, or maybe you've heard them called cuts or something like that. So resistors are zigzags. Okay, let's zoom out for a minute and see what else do we have going on. So of course, a real life battery, and then match it to its symbol. A resistor, and we can match it to its symbol. And light bulbs match it to their symbol. Now, we're not going to talk a lot about LEDs, although they're super common. LEDs are a special kind of light bulb that gives off light from a piece of equipment called a diode. right, their name is a light emitting diode, and it has a special symbol. And these light bulbs are probably what are in, well, they're going to be in cars headlights. They're going to be in cars brake lights. They're going to be in flashlights these days. Even the screen of your television in your family's living room has LEDs in it to light things up. Okay, so those are kind of how we draw circuits. And right, you can see in this picture, here's our energy supply. And then these are considered things that turn the energy into something else. We don't really need to learn the symbol for a wire. It's just a straight line, okay? So let's go ahead and keep going with the lesson, but jump to the next.
Prediction. If this is a circuit with a battery and that has a voltage, and you have a light bulb that's screwed in, and then a light bulb that's taken out of its socket, will that light up at all? Will that circuit light up? Who can predict? If you unplug one light bulb, have you ever done this with holiday lights or like Christmas lights? What happens? Light up or not? This one will not light up because it's missing a bulb. Number two, oh, go ahead, Alex. We're a couple of pages ahead. Sorry, I did jump. Thank you for asking. We're only going to do this one. How about Mr. Devon? Is he still there? Is he still giving us his best effort? Number two, will number two light up? Will this circuit, if you have a voltage and you have two light bulbs that work, but this one's on one side and this one's on the other, is that going to create a circuit that lights up? Yes or no? No light or yes light? Almost. It has to be a closed circuit. Don't worry about getting it wrong. We would need to add one more wire. So do you see? Thank you for sticking with right to the end. Do you see right how there's a missing wire between the two light bulbs? We need to have a battery, we need to have a bulb, and we have to have a continuous pathway. And so this is another example of it's not so much that it's broken, it's just not, right? No light will light up. And we'll come back to a few of these, and we'll see what will happen with this guy. We'll see what happens with this one, and we'll kind of analyze a couple of these next Tuesday. So have a great Memorial Day weekend, guys. Thank you for trying. Thank you for being here. Take care. Bye, Alex. Bye, Cash. Is Cash still there?
Picture. So we're going to do this in class, but the challenge here is to figure out, is the circuit complete or is the circuit open? So it's referred to as an open circuit if there is a break in the loop, right? It has to be a continuous loop from the battery through the wires to the bulb. It's called a closed circuit, and that means there is a continuous loop, and the light bulb will light. So a closed circuit is basically a working circuit. Open is one that's not working currently, right? There's some break in it. So what you would do is you'd go through each of these scenarios and you double check everything. Okay, does that wire look like it's hooked up? Yep, it's hooked up to the battery. Okay, the wire goes to one side of the light bulb, goes to the other side, check. That means in this base, it's going through just like that. And then it goes through another wire. Okay, that's fine. But then here's the problem. That light bulb's unscrewed or someone took it out of its socket. And so now the electricity cannot get from here to here. And so this is a no light situation, right? No electricity will flow if you do not have a complete circuit, complete loop. Let's try number 2. We're not going to do all of them because we're going to do some in class. Okay, is the wire hooked up to the high energy supply? Yep. Wire to the first side of the bulb? Correct. The bulb, we assume the bulb is not broken, but the wires inside, right, are good. And then you notice this gap. There's a space between the 2 light bulbs. But the wire on the other side seems to be good. It would go through this light bulb. But the problem is it is open. There is an opening right here, right? No wire. So if there's no wire to close the loop, there is no light. Okay, will it light up? Nope, no light at all. Okay. Now, let's try number 3. We'll stop after 3. I said 2, but we'll go one more. Okay. So let's look for, let's start with this battery. We got 2 batteries. There's one. We got a wire coming out of our positive. Okay, it looks like it's connected, and it goes to the negative. We haven't talked about that. What if you have 2 batteries? As it turns out, the 2 batteries, you have to think of them as facing the same way in the wire. They have to push the electrons the same way. So if you hook up positive to negative, you're doing great. And it looks like it's connected. And then it comes out of here positive, goes to the light bulb. The light bulb has its filament, and it goes to the other side. Whoa, this looks like our first circuit that is perfectly fine, meaning this thing's going to light up. And we know that because there's a complete loop. We have our energy supply, and we have, in this case, we have 2 energy supplies, and they're pushing in the same direction. Okay. In class, we'll talk about 4, 5, and 6 during our Zoom sessions. Okay, let's zoom out a little bit. Here's one brief mention. Even though this is a long thing to read, what happens if you have a battery and you have wires and you have a resistor? Oh, that's a device that can be put into a circuit. And if that was the circuit, it would be A-okay. It would be perfect. All would be good, right? Here's the problem. Along comes your friend who thinks they know what they're doing with electricity, and they take another wire and they hook it up so it goes around the resistor. And this is going to create a low resistance path because this pathway has no resistor. Has anyone ever heard, and maybe not a lot of you, the path of least resistance? Sometimes people take that. When they see that there's an easier job to be done, they won't do the hard work. They'll take the least resistance. But we're talking electricity here. It doesn't make choices. But what it will always do is it will take the path with no resistance, okay? It just does. And that means this resistor is skipped. It's missing. The electricity is going to go up, around, through the wire, come back, and it's going to have no resistance. So we call that a low resistance pathway. Well, when you lower the resistance, you increase the current big time, and it leads to potentially an emergency or damage to the battery. So we call this a short circuit. It's not about short length, but it is a wire that skips the circuit. But really, it's easy to remember. If there is no bulb or no resistor of any sort, no motor, nothing, and you just hook a battery up to itself almost, right? You can think of it as from the positive all the way through a wire and back to itself. You have a potential for an emergency. This is how batteries, that's not how you spell the word emergency. Let's fix that. What was that? Emergency. Because the battery will overheat and it may even catch on fire. And this has happened in some people's laptop batteries. Hopefully it doesn't happen to anyone you know. But an old battery or a battery that's been abused often will have shorts in it. Okay, last lesson for today is this guy. Let's go next page. Series circuits, okay? We've actually introduced these already. We've got our battery. We're using our schematic picture. We've got our electron dudes, and they're carrying energy. And they drop off some energy here, right? They leave energy behind. Then they carry what's remaining of their energy. See how they only have one little bucket now? Every electron had 2 units of energy. They actually have like half as much now. And then they lose, right? They leave some energy here at the second resistor. That's a resistor. It's got a lot of wiggles in it. And they always come back empty-handed with no energy. So that is a series circuit. Notice the pathway never splits. And that's going to lead us to some calculations you can do with circuits. And I'm going to ask everyone to watch and then try this. It's pretty straightforward. Okay, let me clean up some of this. Okay, the first thing you do when you're analyzing a circuit and you're trying to figure out how it works and what's going on, let's clean up everything, is you simply go in, and we'll do with this practice problem right here at the top, is you try to figure out what kind of circuit it is. Is it series? Or is it its cousin type, which we haven't even learned about yet, called parallel circuits? And the answer is, well, it's definitely series because we haven't learned about parallel. So let's start there. So here it goes. If you see one circuit right after another, and it can be 2 of them, it can be 3 of them, it could be 23,000 of them, but as long as there is no split in the pathway, that's a series circuit. And there's a formula for finding the total resistance. If someone said, what is the total resistance of the circuit? In series, it's a simple formula. It's nothing more than the total if you add them each up. So, and by the way, you'll notice I'll write that RS or RT. T stands for total, but S stands for series. So it's a total of a series circuit. Sorry if I'm not perfectly consistent. I bet you get both ideas. 12 is the first resistor, and that symbol looks like an upside down horseshoe. It's pronounced ohms, and that's how you measure resistance. And then you add it to 4, and then you add it to 6. And with a calculator, you can do all of that in one calculation, 12 plus 4 plus 6, and the total comes out to be 22 ohms. That's how you pronounce that. Again, unit for resistance. So the total resistance is nothing more than the sum. And that's the first step to analyzing a circuit. Always do it first. Okay, so for these circuits, there's 2 below. I want you to find the total resistance of this whole circuit. Okay, so there it is. I see my first unknown goes in. Basically, you're solving this table, and you have to figure out what formula do I use. Oh, I remember that's R1 plus R2 plus R3, or 2 plus 4 plus 1. Super easy, right? 2 plus 4, that's 6. 6 plus 1, 7 ohms of resistance. Okay, now here's where things get a little tricky. You haven't learned yet the formula for total current. And what I mean by that is there's this new law. It's brand new to us, and it's about all of the parts of a circuit. And the formula is called Ohm's law. Ohm's law. Yeah, it's the same unit as resistance, right? Ohms. But Ohm's law says that you take the voltage, which is the energy supply, which is the push, and you divide it by the resistance, the opposite of voltage. And when you figure out that ratio, all it is division, right? Number on top divided by number on the bottom. You totally get the current. So let's see how this would work. So I know the voltage of my battery. And how do I know that? It's just labeled. It's sitting right next to the symbol. I have to remember the symbol for a battery. And it says 14 volts. So I'll put 14 on top. And my resistance is 7 ohms. Oh, I can do that. Just look at the numbers. Just cover up the units for a second. 14 divided by 7. That's something you can check on your calculator, but it should come out to be 2, because 14 is double of 7. Now here's the hard part. Volts divided by ohms will always give you the unit for current, or amps. And that's just a memory thing, learning that the unit for current, right? And here's our final answer, 2 amps. And we just abbreviate capital A. Now remember the story that a series circuit has one pathway, never breaks. Just, right, if I'm an electron, I'm going this way and I'm going straight through and I come back. See how there's no branching? What that tells me right off the bat is that the current right here is 2 amperes. It would be 2 amperes here, because current is like water. If you don't split it like a fork in a river, it's going to stay the same. So all the resistors each get 2 amperes. And that's always true for series circuits. Okay, how do you finish this puzzle? How do you finish this darn problem? Okay, the last step you do is you figure out the voltage drop or the energy drop at each of those resistors. This is where it's going to get a little interesting. Well, remember Ohm's law. If someone said Ohm's law works not just for the whole circuit, but for each individual resistor, but we know the current and we know the resistance, how would you get V alone? Some of us remember that to get V alone, we would move the R to the other side by multiplying by R, and we've got a new formula, V equals I times R. And now for each row, think of it a little bit like Sudoku. The voltage is 2 amps, because that's the current right here for the first resistor, times 2 ohms. So what you do is you stay in a row in this table now, and 2 times 2 is 4 volts. Then you have to do that again for the next resistor. V equals I times R, 2 amperes times 4 ohms. See how it says 4 now in the second row, 2 times 4, or 8 volts. And I bet you can do the last one in your head. It's current, 2 amps, times resistance, which is 1 for that third resistor, and you just multiply the numbers, 2 times 1, or 2 volts. And look what happens. This is going to be not a big surprise. Add up all your voltages, and they better come out to be the voltage of your battery. 8 plus 2 is 10. 10 plus 4, perfect. It worked out. So I will not be showing how to get the final answers for this the answers for this table, because I want you guys to try it with some independence. But remember, step 1, do this first. How did we do it? We added up our resistors. Step 2, I equals V over R. And remember, your unit comes out to be amperes. Step 3, everyone gets the same current because we're not splitting our electricity. And then step 4, let's use this new form called Ohm's law. See how we learned it over here? We divided both sides by R, V equals I times R, and you stay within your row and you calculate your voltage of each resistor by multiplying I times R. Thanks a lot, guys, and that will wrap it up.